Chapter 3, Segment 4. The Site of Selective Adaptation Effects. Orientation and spatial frequency are coded by neurons somewhere in the human visual system. Cats and monkeys have these neurons located in the striate cortex, not the retina. And they can be located in humans with a variation of adaptation experiments. So this experiment occurs when you repeat orientation and spatial frequency adaptation demonstration, but this time view the adapting stimuli only with your left eye and then only with your right eye. And you should find that the tilt after effect and the decreased contrast sensitivity transfer from one eye to the other. This transfer is known as interocular transfer. Information from the two eyes is kept completely separate in the retinas and the two LGNs. No single neuron receives input from both eyes until the striate cortex. The transfer of adaptation implies that selective adaptation occurs in cortical neurons. So spatial frequency tuned patterns analyzers in human vision. They found that human CSF actually reflects the sensitivity of multiple individual pattern analyzers implemented by ensembles of cortical neurons. So each set of cells tuned to a limited range of spatial frequencies and orientations. This is referred to as spatial frequency channels. So multiple spatial frequency model of vision implies that spatial frequencies that stimulate different pattern analyzers will be detected independently even if the different frequencies are combined into the same image. So Graham and Nachmius found that the contrast sensitivity for this compound pattern was almost the same as the contrast sensitivity for detecting the individual components of the patterns separately. So the visual system doesn't carry out the actual Fourier analysis, analyzing the world into very narrow bands of spatial frequencies. Rather, it filters the image into spatially localized receptive fields that have a limited range of spatial frequencies. Visual system uses spatial frequency filters to analyze images because different spatial frequencies emphasize different types of information. If we want to know how many people are in a scene, we rely on low frequency channels. If we want to know details, we rely on high frequency channels. At the near threshold contrasts, pattern analyzers operating at different scales of analysis are independent. At high contrasts, pattern analyzers do interact. So the development of spatial vision. Visual system is much more developed at birth than previously thought. Robert Fantz did a lot of research with infants, and he found that infants will stare at the more complex scene when looking at two scenes. This is called preferential looking, and it depends on the willingness of babies to stare at stimuli near threshold level. So an alternative approach is to measure visually evoked electrical potentials. These are electrical signals from the brain that are evoked by visual stimuli, and this is done by attaching electrodes to the scalps and measuring the changes in electrical activity that are elicited by the changing visual stimulus. Using this, we can measure an entire contrast sensitivity function in about 10 seconds. So the development of the contrast sensitivity function. The contrast sensitivity may reach nearly adult levels as early as 9 weeks of age. So sensitivity at higher spatial frequencies continues to develop dramatically. The primary postnatal changes in the retina concern differential and macular region. After birth, foveal receptor density and cone outer segment length both increase as foveal cones become thinner and more elongated. Dramatic migration of ganglion cells and internuclear layers from the foveal region as the foveal pit develops during the first 4 months of life. It's not until 4 years of age that the foveal is fully developed.